I'm Donna Dietz. I teach at American University just like Dan Kalman, and sometimes we talk about math even. So if you haven't already, you should make sure you read Dan's Game of Stones article, which is in this month's Math Horizons. And if you were just here for his talk, you heard him talk about this situation. In Dan's game, the dangers are much more severe. There are knights about to be beheaded. I assure you no such dangers lurk in my games, but people could die of embarrassment. The three games I'm going to talk about are three situations which I've personally participated in, unlike Game of Stones. But let's talk about them first, and then I'll go into more depth with the social dangers of each one. First of all, you have the situation where students can grade each other's papers or quizzes. Second situation is some icebreaker games where everyone has to introduce another participant at random. And the third situation is a secret gift giving game in which the same pairings are kept for several cycles of mysterious gifts. These are all really the same mathematically. They all work around permutations and derangements, but they are different socially, and therefore they cause different dangers. First situation is grading each other's papers. This is when, for example, the teacher collects up all the papers and distributes them back to all the students. Is this actually legal? Apparently in 2001 there was some question about this being legal, and it was determined that it was illegal because of FERPA, unless you anonymize all the papers, which the teachers didn't want to do because it was too much work. And the Supreme Court came along the next year and said, never mind, it's okay. The second game is an icebreaker game in which you introduce each other. So you can see me. I'm on the left over there in the black sweater. But the group was bigger than this. But this is us before everybody showed up. And the idea with this is you grab someone's name, and first you spend some time getting to know them. You try to find the person whose name you have and get to know a little bit about them. Meanwhile, somebody's trying to find you. But it all works out, and everybody has a good time. And the third situation is what I'm calling Secret Sister, which is very much like a Secret Santa game, where you repeatedly give little gifts to somebody else until a big reveal happens at the end of the game. In our case, it was 9 months long during a whole academic year. And so you just secretly give things to your secret sister until the end of 9 months, and then they tell you who your secret sister is. It's a nice big party at the end of the school year. Okay. First game, students grading each other's papers. If there are n students, your chances of getting your own paper are 1 over n. From the teacher's perspective, the expected number of self-graders is 1. Maybe what you really want to know is what's the chance that the school bully or the class bully gets your paper, and that's also 1 over n. But what does the distribution look like? If there's 2 students, you can either keep your own papers or swap, and there's a 50-50 chance of randomly having either situation. That's easy. For 3 students, I'm going to assume the students are named A, B, and C. Then there are 6 ways of handing the papers back, and if you hand them back in sequence, everybody grades their own paper, and there's a 17% chance of that happening. Or everybody could sit in a triangle and pass their papers to the right or the left, so there's 2 more situations. And then the remaining 3 situations come from one person hanging on to their paper and the other 2 people switching. So that gives you all the 6 possibilities. And so that's 3 factorial, or 6 ways to arrange the papers. The 4 student case. So hopefully there's no typos, but I typed out all the possible permutations of 4 items and then just visually counted how many things were in the same place and tabulated it. And of course there's only one situation where all 4 students grade their own papers. You can see why there's no situations of 3 self-graders, right? Because if 3 people self-grade, the 4th person has no choice but to self-grade. So there's no situation of n-1 self-graders. And then if you just count these up, you find all the possibilities. We will like to count the number of non-self-grading situations where everybody has a different paper. Do we actually care about self-graders? I mean, after all, if a child gets their own paper, they usually won't be able to resist saying, "Oh my gosh, I got my own paper, I got my own paper," and the teacher's going to be like, "You got to switch papers, you know." And so they'll switch with somebody. And in most games of this nature, self-matching isn't fun at all. Like, you're introducing yourself, that's kind of stupid. Or you giving yourself gifts, that's kind of stupid. So there's usually formal or informal ways of resolving the permutations which are not derangements. And what is a derangement? A derangement is any permutation in which nothing gets to stay in the same place. So we will keep looking at all permutations, but we'll focus on the derangements, because those are the fun situations. Okay, let's go back to the 4-student case and see if we can count the derangements. First of all, how not to do this. You could give student A a paper to grade, that's 3 ways. Then you could give student B a paper to grade. And already the trouble begins. Because if A has B's paper and there's a 1 in 3 chance that that happened, B has 3 options. B could grade A, C, or D. But if A did not grab B's paper, then B can only grab 2 out of the 3 remaining papers. So you get this massive tree diagram that's annoying, and so we're not going to go that direction. Let's try something else. Let's line up all the students randomly, and everybody passes their paper to the right. This worked great with our situation with 3 people, so let's try it again. Everyone passes their paper to the right, and then the person on the end brings their paper to the other side of the line, so it's actually a circle, right? So you have n factorial ways to line everyone up, divided by n, because it really doesn't matter who's at the front of the line. So there's n minus 1 factorial ways to do this. Is this okay? Oh, hold on. That would mean that for 4 students, we would only count 6 derangements, but we counted 9 derangements. So where do the other 3 derangements come from? Right? Hopefully, that's what you're thinking. Okay, so you probably already know, some of you already know what I'm going to say, but I wanted to make this clear that this is one of the points of this talk, is to realize that this is a common logical error, especially if you're dealing with non-mathematicians who don't want to think these through very carefully, and it's kind of amusing. Because if you make a circle of people, that will create a valid derangement, which is perfectly fine for most games. But not every derangement is a single cycle. And that's where the fallacy slips in, because a lot of people will assume that there's a single cycle, especially if they notice that there's a big cycle, they'll assume that there's a single cycle. Okay, so let's talk about the other 4 derangements for a bit. Of the 4 items, you could simply select 2 to swap, and then swap the other 2. And then you have another valid derangement, which is not a single cycle of 4. How many ways are there to do this? Well, you could just say 4 choose 2, but the problem is you have to consider that the other 2 people are also going to get swapped. So if you select A and B, it's identical to selecting C and D. So when you do 4 choose 2, you have to divide by 2 to get rid of the overcounts. Okay? There's formulas that you can use to calculate these things. Thank you, Dan. All right, but I'm going to stick to the numerics. Same process, but using numerics. We're going to look at permutations first by their maximum cycle length. We want to get a first idea without resolving the permutations into strictly derangements. Let's just see what these distributions look like. N equals 2 case, boring. N equals 3 case, okay. So you can have a cycle of 3 or a cycle of 2 and like 1 student self-grading, for example, and 3 people self-grading. Those are the N equals 3 cases, just to think in terms of the students grading papers game. In the N equals 4 case, there's 6 ways you can make a cycle of 4 students, but there's 8 ways you can have 3 people switch papers and 1 person self-grade. There's 9 ways in which you can have a maximum cycle length of 2. And this is, well, you could have 2 swap and 2 swap, or you could have 2 swap and 2 self-graders. And I'm putting them all in the same bin together as a way of saying the maximum cycle length is 2. So that's what we're looking at on these charts. In N equals 5 case, I'm not going to label all of them, but you can see that there's 40 ways for 5 students to do one of 2 things, either split up as a cycle of 3 and a cycle of 2, or a cycle of 3 and 2 self-graders. Okay, so that's what these charts are doing. And if we just keep looking at these as they march along, they make this neat shape. So this is roughly at the halfway point. You see where 40 is, it's halfway. That's the max peak of this here. And then the 2 sides of this graph have these characteristic slopes, and I have no idea what the formula is for the envelope of those curves, but you can just look at them. Okay, so how many permutations are actually derangements? As a first stab, you can assume that they're off by about a factor of 2. So roughly half of the permutations are derangements, which means that asymptotically they are limiting to identical. They're identicals asymptotically. And so this plot shows you the blue chart. This is from Wikipedia. The blue curve is the number of permutations, and the red one is the number of derangements. The green dotted line is just showing you where the curve 10 to the n is on this. Of course, it's a line because it's log paper. So it's just kind of a reference point. We know that the gamma function is much faster. It grows much faster than any exponential function. So nothing surprising there. Now let's look at this at a case-by-case basis. So we're down here at the very bottom. We're going to work our way through this curve case by case for a little while. And for n equals 3, you have only 2 possibly derangements out of the 6 permutations. Okay, and then we have a n equals 4 case. You can see you're getting some more derangements coming in, and you're actually getting another kind of characteristic set of shapes. One thing we notice is that the far right is always going to be a blue bar, because if you have 10 objects and you have a cycle of 10, obviously that's going to be a derangement. That's that cycle case I was talking about. The penultimate bar will always be strictly red, because if you, for example, have 10 objects and you have a cycle of 9 in there, then the last item has to be paired with itself. This bar, except for the n equals 4 case, this will always be half red and half blue, and that makes sense too, because if you're pairing off n minus 2 items, the other 2 items have a 50-50 shot of either being paired or split. And the fourth last bar always has to be 2/3 red for similar reasons. If you have n minus 3 things in a cycle, the remaining 3 things have a 1 in 3 chance of also being their own derangement. So that all makes sense. And finally, this bar on the far left, whether you can see it or not, always has a height of 1, and it's always red. But you see, you basically can't see it anymore, but it's always there. And you keep looking at these plots, and I went up to n equals 50 with that, and you can see that it has its own characteristic shape, which is becoming apparent. Okay, second game, the mom's icebreaker game. So what do you think happened in my case? Why do you think I thought this was interesting? When we got back to the first person, people said, "Oh, I guess we're finished. Let's go on to the next activity. Oh, wait a second. We left a whole bunch of people out." This was really awkward. This was supposed to be an icebreaker game to make everybody feel warm and fuzzy and important and special, and we just left out a whole chunk of people. Okay, so what causes this social danger? My guess here is that everyone being in a single cycle is totally fine, no problems, and that a whole bunch of small cycles is also fine, because once you complete a small cycle, people will start looking for the other cycles. However, if the largest cycle has more than 2/3 of the people in it, the remaining participants are likely to be forgotten. So in a group of 3, not going to happen. Group of 4, 5, not going to happen until you get to, say, 7 people. In this situation, you have 5 people being introduced, and they may forget the other 2 people. That's the first case I'm labeling as dangerous. And likewise with 8 or 9 people, this can happen. 10 people, then you could have 7 people forgetting 3 people, or 8 people forgetting 2 people, things like that. Okay, and we just keep marching along. And I estimate that about, just under 40% of the derangements are dangerous cases. And that's what it looks like. It's kind of limiting there. Of course, you change your definition, that's going to limit to a different level. Okay, the third game. What are the social dangers in the Secret Sister game? In this game, we're trying to keep the identity secret until the end of the game, which is the opposite of the previous game where we tried to find the people we were paired with. And if you bust your own cover by putting things directly on your secret sister's desk, that's your own fault, because a lot of people who are not directly participating in this game, they really love to help you hide things for your secret sister. And so there's no lack of people willing to help you plant secret gifts. However, in this game, you must never, ever, ever what? Never regift. I was really, really tempted because my secret sister gave me some scented soap, which was very lovely, but I don't like scented soap, and I forgot to say that on my survey at the beginning of the game. And so I thought, well, I don't like scented soap, but maybe the person who I'm giving gifts to would like these gifts, would like these scented soaps. And I'm really, really glad I didn't do it, but I was really, really tempted. And that would have totally blown my cover, and that would have been super embarrassing. So if you're playing one of these games, never, ever, ever regift, because you really don't know. What are the chances? For you personally, it's going to be at least 1 over n minus 1. And I say at least because for human reasons, these are not necessarily randomly selected pairings. Okay, so there's often people who join the game late and so on and so forth. And so that increases the chance that cycles of size 2 are going to be formed more likely than if they were just mathematically selected. Okay, so for you as the organizer, the expected value is about 1. That's of course insane. But what does the distribution look like? I'm going to consider a derangement to be safe if there are no cycles of size 2 in the derangement. So if you have a derangement of size 5, 54% are safe. A derangement of size 6 is 60% safe, and it levels off at about 60%. So 60% of derangements of any appreciable size are going to be free of cycles of size 2. In conclusion, derangement games can be socially dangerous. You have been warned. Thank you.